I'm here to talk about homework number 2. So for 2-24, it asks to find the energy balance on a cylindrical shell from a one-dimensional, like you have to derive it. So started with general equation at the top, and then made some appropriate substitutions, and then figured out what Fourier's law was, plugged that in, and then divided everything by 2 pi r delta RL, took the limit as delta R approached 0, and then I derived the equation right there. And then for 2.66, it was a flat plate solar collector, was used to heat water, having water flow through the tubes. So my assumption is that the top face surface is subjected to convection radiation, incident solar radiation. So this is the equation we started with. You integrate it once, and then you integrate again. Apply the appropriate boundary conditions, which are pretty straightforward. So because it's given to us. And then I was a little bit confused here on how we got to solving for Q naught. So I ended up looking up at the solution and I still didn't understand it. Then for question 2-102, we have water and the heating element floating through it. I assume the thermal conductivity is constant, 1D heat transfer. So therefore we started with the 1D heat transfer equation, figured out the boundary conditions, which is convection outer surface and symmetrical thermal center line, rearranged, integrated, applied the boundary conditions in the appropriate places, and then used the boundary condition, and then we were able to solve for what t was as a function of the radius, and then plugged in appropriate values and got that value there. And then for 1440, which was water, I think sitting in it was water sitting in a room. And the assumptions were that it was ideal gas, and I believe Henry's law can be applicable to the situation. So then able to determine that the saturation temperature of water 50 degrees Celsius was that pressure, and this was because the air was saturated, and then we were able to solve for what Y of the vapor was. And then since the total pressure was 97 kilopascals, the partial pressure of the dry air was just like a simple subtraction problem that we were able to do. And then so therefore we were able to figure that out. And then from Henry's law, the mole fraction of the air in the water was determined to be this value, which we were able to figure out.